In this video, we're going to define the derivative and talk about its relationship to a function's instantaneous rate of change as well as the slope of the tangent line. So here is our definition. If f is a continuous function over an open interval and c is a point in that interval, then the derivative of f at c, denoted by f prime c, is equal to the limit as h approaches 0 of f of c plus h minus f of c divided by h. So this is the derivative as long as that limit exists and is finite. If that limit exists and is finite, we say that f is differentiable at the point c. Otherwise, we say that f is not differentiable at c. And if f is differentiable at all points in that open interval, then f is differentiable on I, that interval. So that's quite a mouthful. Let's now see where that definition comes from and try to make sense of that definition. So recall that in the very first video of this course, we talked about the average rate of change of a function and the instantaneous rate of change of a function. And we said that the average rate of change of a function from a point x equals a to x equals b is given by the slope of the secant line between those 2 points. So here's my function, and I'm drawing a straight line, hopefully, between those 2 points a and b. And the slope of this line is equal to the average rate of change over that interval. So the slope from x equals a to x equals b is equal to the change in y over change in x, which is equal to f of b minus f of a divided by b minus a, the change in output over the change in input, and each of those things is going to be equal to the slope of the line between the points a, f of a, and b, f of b. The instantaneous rate of change of a function at a point x equals c is given by the slope of the tangent line to the curve at c. So again, we're trying to draw a straight line, doing our best. It's not too bad. That's the slope of the tangent line at the value c. So slope of tangent line at x equals c, and that is our instantaneous rate of change, the speed at which the function is changing at that moment. And before, when we introduced this video in the first video of this idea in the first video in the course, we didn't have the tools to actually calculate this instantaneous rate of change, and instead we estimated the instantaneous rate of change. We estimated the slope of the tangent line by selecting a point like c plus h for a value that was very close to c, and say, okay, we're going to instead find the slope of the line between those 2 points and use that slope to estimate the slope of the tangent line at c. So it's not an exact value, but depending on how close a value to c we picked, we would get a closer and closer and closer estimate. So now we've talked about limits, and now that we understand limits, we can actually find the exact value of the slope of the tangent line at x equals c, which is the same thing as the instantaneous rate of change of the function at x equals c, which is the same thing as the derivative of the function f of x at x equals c. So all these things are the same. And each of these things is given by what we call now the derivative f prime of c equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. So let's just see where that comes from. So as we said, the instantaneous rate of a function is given by the slope of the tangent line at c. Previously, we estimated that slope by selecting some point h, and it could be, a negative value or a positive value, so c plus h. Here h is less than 0. And we're saying, okay, we want to estimate the slope of the tangent line by picking that point and then finding the value of the slope between those 2 points. So our estimate is estimate of slope of tangent is then given by, again, the change in y over change in x. And so that's f of, we could do either c plus h, we can do them in either order, f of c plus h minus f of c divided by c plus h minus c. So we've got the change in output over the change in input. And we've got, again, the point, this is the point c f of c, and this is the point c plus h f of c plus h. So we've just got change in y over change of x, change in output over change in input. Okay, so previously we did that by saying, okay, let's let h be small. H could be negative 0.1, or h could be 0.01, or h could be negative 0.0001. We can make h smaller and smaller, and the smaller the value we chose for h, the closer we were to the actual instantaneous rate of change, the actual slope of the tangent line. But now we have a new tool at our disposal, and that tool is limits. So instead of estimating the slope of the tangent line, we can find the exact slope of the tangent line. And to do that, we can use limits. It should be equal to the limit as h approaches 0 of f of c plus h minus f of c divided by c plus h minus c. So again, that's change in output over change in input. And instead of saying, let's pick small values for h, let's get smaller and smaller and smaller, we are getting as small as we can. We are taking the limit as h approaches 0, so h is becoming infinitesimally small, and saying, what does that value equal as h goes to 0? And so that's pretty close to the definition of the derivative we have up above. The one difference is that this c and negative c cancel out with each other, and so we've got the limit as h approaches 0 of f of c plus h minus f of c divided by c's cancel, so just h is left on the bottom, and that is our definition of the derivative at the point c. That is f prime of c. And again, that's equivalent to the derivative of f at c, the instantaneous rate of change of f at c, and the slope of the tangent line of f at c. So let's do an example where we use this definition of the derivative to find the derivative of a particular function at some specific points. So we know that f prime of c is equal to the limit as h goes to 0 of f of c plus h minus f of c divided by c plus h minus c, which is just h. And so let's find that for this particular function f of x. So in this case, this would be the limit as h goes to 0, and we're going to do it for here c equals 2 first. So it would be f of 2 plus h minus f of 2 divided by h. And so now let's plug some values in. So this is the limit as h goes to 0 of, now I'm actually thinking about what is my function f of x. So this is x, the input squared. 2 plus h squared is the first term in f of x, minus 2 times the input, 2 times 2 plus h, and then minus f of 2. So I could either do that on the side or plug in all in there. Let's just do it on the side, partly because we're running out of space. If we say what's f of 2, f of 2 is equal to 2 squared minus 2 times 2. So just plugging in 2 for x. And so that happens to be 4 minus 4, that happens to be 0. So that happens to be kind of easy this time, divided by h. And then we can continue to simplify. This is equal to the limit as h goes to 0 of now 2 plus h squared. Again, we can do that on the side too. There's absolutely no shame in doing your algebra out on the side. So 2 plus h squared is equal to 2 plus h times 2 plus h, and that's equal to firsts 4, 2 times 2, plus 2h outers plus 2h inners plus h squared. So that's 4 plus 4h plus h squared. So our first term, just expanding the 2 plus h squared gives us 4 plus 4h plus h squared. And then let's look at our second term, 2 times 2 plus h. That's negative 4 minus 2 times h, so minus 2h. And then 0, of course, just simplifies to 0. And we can keep simplifying that. That's equal to the limit as h goes to 0 of, well, let's see, the 4's cancel out. And then we've got 4h minus 2h, so that's 2h plus h squared, still divided by h. And now I could factor in h out of everything in both the top and the bottom. So this is the limit as h goes to 0 of h times 2 plus h over h. And now I could cancel my h's. And what I'm left with is the limit as h goes to 0 of 2 plus h. And now that's something I can just plug 0 right into. That is 2. So that's telling me that 2 is equal to f prime of 2. Just a coincidence in this case that the derivative at 2 happens to be equal to 2. Okay, let's now find the derivative of the same function at the value x equals negative 1. So again, we're using the limit as h approaches 0 of f of c plus h. C in this case is negative 1 plus h minus f of c, that's negative 1, divided by c plus h minus c, which is just h. That's our definition of the derivative. And so that in this case is equal to the limit as h approaches 0 of f of negative 1 plus h. So using again just what our function is defined as, we're plugging in negative 1 plus h into x for x squared. So negative 1 plus h squared minus 2 times negative 1 plus h. So all of that was just f of negative 1 plus h. So it's f of negative 1 plus h minus f of 1, or sorry, f of negative 1, and then all divided by h. So now we could keep simplifying this. This is the limit as h goes to 0. And I like to do my simplifying on the side, so let's keep doing that. Negative 1 plus h squared is negative 1 plus h times negative 1 plus h, and that's equal to negative 1 times itself is positive 1, minus h plus h squared. So that's 1 minus 2h plus h squared. So that's the first term, negative 1 plus h squared is 1 minus 2h plus h squared. Now our second term, we've got negative 2 times negative 1 plus h. So negative 2 times negative 1 is positive 2, minus 2h, so minus 2h. And then we've also got f of negative 1. So f of negative 1 is negative 1 squared minus 2 times negative 1. And so that's negative 1 squared is positive 1, minus 2 times negative 1, that's plus 2, so that's 3. And now we can plug that value in. We've got minus f of negative 1, so minus 3, all divided by h. And now let's see if anything cancels nicely. We've got 1 plus 2, that's 3 minus 3. Those cancel out with each other. And then we could also combine the negative 2 h's. So let's just simplify what we've got so far. This is the limit as h goes to 0 of, the constants are gone, negative 2h minus 2h, that's minus 4h, plus h squared divided by h. And so, again, we can factor an h out of the top. We've got the limit as h goes to 0 of h times negative 4 plus h divided by h. And that gives us, well, again, the h's cancel out. So we're left with the limit as h goes to 0 of negative 4 plus h over 1, which is just negative 4 plus h. And now we can plug in, because we don't have any issues with zeros in the denominator. So now we can just plug in h equals 0, and now we've got our limit is negative 4. And that is f prime of negative 1, the derivative of the function at x equals negative 1. Okay, so let's think about back to the 3 different interpretations of the derivative. So we saw before that the slope of the tangent line of the function is equal to the instantaneous rate of change of the function at that point and equal to the derivative of the function at c. So f prime of c is equal to each of those things. Let's just see this in terms of, we've looked at the definition of the derivative. Let's think about the slope of the tangent line and the instantaneous rate of the change of this function that we've been working with. F of x equals x squared minus 2x. So above, we found that f prime of 2 is 2 and f prime of negative 1 is negative 4. So f prime of 2, that's the rate of change of the function at x equals 2. And that should be equal to the slope of the tangent line at x equals 2. And so, yeah, that seems believable. So the slope of the tangent line at x equals 2, for every 1 we're going over in x, we're going up 2 in y. So yes, that's a slope of